Hi, hello everyone. So I'm giving this talk on behalf of Haiyang, who couldn't be here today, not because of the train strike, but because he's in China. Okay, so we thought we'd start off by sort of talking a bit about, the motivation for even attempting to develop a magma reservoir simulator. And we've seen today, in some great talks that we have, and in other conferences that we have, these very extensive petrological and geochemical data sets now from both modern and ancient magmatic systems, and they're really powerful in giving us sort of ideas of how chemical differentiation is occurring and the rates and timescales of the processes that are happening and where that's happening, the depths and the temperatures. And we also have geophysical data that provide a snapshot of modern magmatic systems. And then what we try and do is to interpret those data to produce models of the coupled physical and chemical processes that operate in magmatic systems that give rise to those measured data sets. And so they're often interpreted in terms of fractional crystallization or crustal assimilation, thermal rejuvenation, magma mixing, and so forth. And I think the issue here is that it's not always clear that, we know that a comment was made to this effect this morning, that we know that these systems must obey sort of basic physics and chemical laws. And it's not often clear that we are obeying those laws when we develop conceptual models of how we think the systems are operating. And if we look at other areas of earth science and earth engineering, it's very common where you have sort of sparse data sets that you want to integrate across data sets of different types that maybe have different length scales and time scales of resolution, to try and integrate across those by using quantitative numerical models that try and capture the relevant physical and chemical processes. So there's lots of examples in, for example, subsurface hydrology, CO2 storage, climate models and weather models. The data are interpreted and predictions are made based on quantitative models, by which I mean models where we try and formulate a set of self-consistent equations and solve them, typically using numerical methods. Now we do have, some quantitative models of crustal magmatic systems, which, go back several decades now. And they often sort of simplify and separate out some of the important processes. Particularly, we often see models where we look only at thermal kind of aspects. So we see thermal balance and thermal conduction and how that impacts on the thermal regime in the crust. And then we have some models that look at sort of fluid dynamical processes, and often those are looked at separately. And I think that's not, and I'll show you an example of why I don't think that works very well in just a minute. But we also see now recently kind of a real emphasis on understanding reactive flow, so coupling together fluid dynamical processes and chemical reactions as giving rise to some important processes in crustal magmatic systems. So in terms of thermal modeling versus modeling that involves some fluid dynamics, this is quite an old bit of modeling now. I just wanted to show it as an example. We're going to look at what happens if we intrude basaltic sills into the crust repetitively. So it's kind of a type of model that Catherine Allen published quite a few years ago. We'll look at the temperature as a function of depth on the left panel, look at melt fraction in the middle, and we'll look at silica content on the right. So we're going to intrude sills into an initially intermediate composition crust. So as we expect, as we start to intrude sills, we see little spikes of temperature as those sills come in. Initially, they cool really fast because they're surrounded by cold rock. And so Catherine called this the incubation period. We don't actually have a magmatic system here. We just have a series of sills which have cooled very, very quickly. And we don't see any differentiation because, of course, a purely thermal model can't capture the separation of melting crystals. So you have quite a long period where nothing is really happening other than we're just intruding basaltic sills and we're gradually warming up the crust as we go through this incubation period. And eventually we reach the point where we start to see melt being present in between sill intrusions, but except for the very transient period where just after the sill intrusion has happened, the melt fraction still stays pretty low. And so one of the models you might have now for sort of extracting magma is to say that if the melt fraction exceeds this sort of solid to liquid transition, then we can erupt that magma. But we're not really seeing any persistent magma present, which does in fact exceed that solid to liquid transition. And so in a thermal model, what you'd say is, well, let's intrude faster, let's make it hotter, and then we can get the melt fraction up high enough to actually produce large volumes of eruptible magma. And in fact, here, the highest melt fractions we're seeing are where we've partially melted the pre-existing crust, because that's more fertile than the intruding basalt. So we don't really produce any magma from this system. Now, if we look at the same model, that's kind of a snapshot towards the end of the system life, and we don't really get close to that solid to liquid transition. If we look at the same model, but now we allow melt crystal separation, so we put a bit of fluid dynamics in there. The first thing we see is that even within each individual sill intrusion, we get bits of differentiation occurring in the individual sills. So we're getting ill-evolved caps and more refractory bases because we're seeing melt crystal separation in each intruding sill. We still go through this incubation period. We've got to warm the crust up to actually produce a persistent magma reservoir. But we start to see much more variability in composition already on the right-hand side. And eventually we're going to produce a persistent magma reservoir, and we're going to see that then melt can percolate upwards through the mush that's produced. The melt's buoyant, the mush is permeable, and we can start to migrate that melt upwards. You can kind of start to see it kind of starts rolling upwards. You can see in the silica there, you can see little lenses of melt that are rolling upwards through the mush, and that means that we start to accumulate melt at the top of this magma reservoir now, and that's much higher. The melt fractions are much higher than the solid to liquid transition. So we can imagine this as being eruptible magma that could leave the reservoir, and it's also very silicic. So the process of melt percolating upwards has been accompanied by a reaction. We've had reactive flow, which has evolved the composition of the melt, and so we end up with a sort of an evolved silicic cap that sits on top of quite a thick kind of mush layer, and that's kind of something we see quite often in conceptual models. So completely different behavior if we put in some fluid dynamics versus if we leave the fluid dynamics out and just look at the thermal response. And that's kind of the final configuration we got there with this high melt fraction lens sitting on, which is of silicic magma sitting on top of quite a thick column of low melt fraction mush, the kind of thing you might see in geophysics. So that's not enough though. That was all 1D, and there was plenty of physics and chemistry we didn't capture in there. So what should a magma reservoir simulator try and capture? So this is kind of a schematic of what we might expect to have in a magma reservoir. We've got some high melt fraction regions, we have some low melt fraction regions, we've got some recent intrusions of parent or magma, we've got some layers of accumulated magma that have perhaps been created by this percolative reactive flow through the mush. This is a very challenging system to model, particularly trying to span the fluid dynamics of the high melt fraction regions and the low melt fraction regions. And I think there's a lot of dynamism in there that's not captured by this figure. So we would expect some of those layers to be buoyant. They would start to work well. We wouldn't have these very flat layers. We could see coalescence of layers as we get upwelling and large scale convection. And we don't have any volatiles in here either. So adding volatiles is another sort of level of complexity. So we have a lot of kind of complex coupled physical and chemical processes that we want to try and capture in a magma reservoir simulator. So we've been trying to do this by extending an existing open source code that we developed at Imperial called IC-FEMRES, the Imperial College Finite Element Reservoir Simulator, and we developed that originally to look at porous media flow problems like subsurface hydrology and CO2 storage, energy storage, and so forth. And one of the nice things about the simulator, we're having to simulate here in a large domain, but we want to be able to resolve small features where we can. And one of the ways we do that is by using a mesh to discretize space that actually changes during a simulation to put more resolution where we have lots of interesting things happening and lower resolution elsewhere. And this is just an example of using that mesh adaptivity to capture dense fingers of salty water sinking down in aquifer from an upper layer of salt water. In terms of modeling magma reservoirs, we assume the reservoir can contain salt, solid and melt, and also a volatile phase. I'll just touch on volatiles at the end of the talk. We assume that all the phases are Newtonian fluids, which I realise is already a simplification, but with a very large viscosity contrast between, say, the deforming mush, the magma, and the volatile phase. And where we have flow, we assume that we can model that as a Stokes, a creeping flow, during both shear and compaction, and then we're going to have porous flow of melt at low melt fraction, and then a sort of a hindered settling type model at high melt fraction. And we have buoyancy can drive flow of all of those phases. So, and we've sort of taken some ideas from Tobias's work looking at this. You know, he was pioneering these ideas around how we can develop coupling terms and models for the material properties that would span the low melt fraction range, the high melt fraction range. This is just an example of a coupling between liquid and solid velocities, where we design this coupling to try and span those different melt fraction domains. So we conserve heat, mass and components. That's something we really want to do. We have heat transport by advection and conduction. We have mass and component transport by advection, both with the melt and the solid phases, and also with the volatile phase. And then we also want to be able to model melting and freezing and component exchange. And we do this using a chemical model that we can kind of plug in. So it's not built into the simulator. It's something which can come in from the outside. And that needs to be robust, so we always need to get a solution that works. If it fails, the whole simulation will fail, and it needs to be really fast because we have to calculate the chemical exchanges at every time step in every element of the model, which means that we're looking at doing tens to hundreds of millions of chemical calculations in a simulation. So what we're doing at the moment is using essentially a simple phase diagram. We can track silica content. The phase diagram is built from melting experiments on basalt and dacite rock samples. So we can build a solidus curve and a liquidus curve. And that allows us to then allows us to model component exchange, modeling silica exchange between the solid and the melt phases. And it allows us to build these melt fractions as a function of temperature curves for every bulk composition that we might see. So as soon as we have melt-solid separation here, then the bulk composition can start to change in the system. That means that we need to account for that when we're looking at the phase equilibrium. We can't use a single melt fraction versus temperature curve because that doesn't account for the reactive flow that changes the bulk composition. So we've got some validations of this. The typical way of taking a code like this and then testing it is to look at some simplified physics where we can look at some analytical or semi-analytical solutions that capture some of the physics of interest. So this is looking at the pure compaction problem where we can use Dan Mackenzie's solutions, and our numerical solutions in the crosses, and the lines are the semi-analytical solutions. We can get a good match there. And this is just looking at another example where we look at conductive heat transfer with melting. And again, the numerical solutions are in blue and the analytical solutions are in red. So we see a good match, and we've got other tests that we've done that I don't have time to show here. So just a quick kind of early result. This is a new toy. We've only just started playing with it. So looking at what might happen in a magma chamber in 2D, not the 1D simulations I was showing earlier. And I'm going to show you two different cases. So we've got this magma chamber. It's initially fully liquid, or I think it's got 5% crystals. And we're going to let it cool and crystallize and look at the dynamics that might happen in there. So the upper panel shows melt fraction, and the lower panel shows silica content. So what we see is that the system starts to cool, so the melt fraction starts to go down. But of course, the melt tends to move upwards because it's buoyant. So we've got a combination of crystal settling and compaction that's squeezing the melt out towards the top. And compaction reactive flow is giving rise to this evolved lens at the top of the sort of more silicic layer at the top of the magma chamber, and we're leaving a more sort of cumulate layer behind, which is more refractory. So this kind of looks like that classical kind of differentiation thing I talked about at the beginning, where we can get this more evolved top and a more refractory base in a particular magma chamber or sill intrusion. But we only have to tweak the shear viscosity of the mush a little bit, and we see something completely different. So the same starting condition, but now it looks quite similar to start with the cooling. But now we start to see some instabilities forming. So we've got these radial instabilities. So we start to see downwards moving plumes and quite active convection happening within the system, which starts to really stir things up and change that simple model of an evolved cap and a more refractory base. So a much more dynamic system with far more kind of mixing of components, but even then, that kind of mixing process is quite complicated. So if we kind of zoom in, we can look at the phase separation velocity. So this is the velocity with which the melt is moving with respect to the solid phase. So where it's red, it means we have lots of segregation. The melt's moving up and the crystals are moving down. That tends to happen in the upwelling part of the plumes. But in the downwelling plumes, there's almost no separation of melt and crystals. So those crystals are going to be experiencing very different chemical conditions. In this part of the system, they're actually quite happily sat with some melt that's moving with them. Whereas in this part of the system, they're experiencing very different melt conditions all the time. Right. So I'm just going to very briefly talk about volatiles. So we have been looking at bringing volatiles into the system. This is looking at the sill that's cooling and crystallizing. But this time we're able to bring a volatile phase out of, oh, sorry. Bring the volatile phase where it's dissolved in the melt, it can dissolve, and we start to see some quite complicated behavior, which is the third column from the left. That's showing us the free volatile phase. We start to see a sort of an accumulation of volatiles at the top of this sill. As they migrate upwards, which starts to in fact inhibit the movement of melt, and we don't start to accumulate melt at the top of the system in the same way. And I have completely run out of time now, so I will stop talking.